Thank you so much for joining. My name is Kolani Ndlovu, popularly known as Mr. X. I'm a very passionate man with mathematics and physical sciences. This is what I teach for grade 12s, all the way down again to grade 10. So welcome to this free lesson. We are going to do work, energy, and power, just the parts that are very essential. Now, I must say that it's not going to be fully exhaustive because there's more stuff that I would want to do, but I can only do a 2-hour lesson. So I hope you guys can be able to enjoy. I hope that we can also be able to ask as many questions so that whatever you do not understand, you can be able to understand. Now, if you want to know more about me, I have a YouTube channel, Mr. X, Mathematics and Science, grade 12. That's my YouTube channel name. Also, as well, you can be able to access me, and I'll give you my number as we come through. I am teaching in quite a big school, but also I run my own tutoring lessons. So what I do is I tutor large numbers of people online or face-to-face, and I'll give you all the details as we go towards the end of the lesson on this one. All right, so I'm ready. We can start. Video is going to be deactivated. You will be able to hear me out, and this is what we're doing. Today's topic, work, energy, and power. That's what we're dealing with. Work, energy, and power. Get your books out, your pens ready, the important stuff that is needed, and we start on that aspect. Good. All right. Now, so to begin with, we need to talk about work. This topic is threefold. So we start with the concept of work. What is work in physics? First point says the work is done when a force acts on an object and it causes the object to, and I'm finishing up, to move some distance from the start point, also called displacement. So let me clarify this. So work is done by forces. This is very important. In the absence of a force, there is no work done. And so to do work, I need to have a force. And not just that, but the force must have the ability to move the object some distance. And in physics, we say displacement. So I have an object, that's true. There is a force acting on it, that's true. Is the object moving? Yes. In that case, if this is the object and there is a force acting on it, and the force causes the object to move. To move means to change position. It's at position A currently, and it's going to go to position B. So the object will move from A to B some distance from the start point. The object will displace. And when that happens, we conclude that work is done. There must be a force, and the force must cause the displacement. Now, again, just to reiterate this particular thing, it's important to understand that without displacement, there can never be any work done. There must be a displacement, a movement that is caused by the force acting. Then we can qualify to having said that work is done on that particular object. So here's again a scenario that is the same connotations. As you can see for yourself, there is that particular object right there. And this object has got force acting on it. And the object moved, the object displaced. And we say work is done. That's very important to pull through from there on. The amount of work done depends on two things. It depends on the magnitude of the force. Please note these important things. It depends on the magnitude of the force as well as the displacement of the object. How big is the force acting and how far is the object moving? Those two important points will give you an indication of how much work is done. So the amount of work depends, number one, on the magnitude. The word magnitude in science means size. It means amount. It means quantity. It's the value. I want to know the magnitude of the force. If it's a high magnitude, if it's a greater size, a bigger force, then the amount of work increases. Also, we consider the displacement of the object, how far the object moved. So let me write this down so that everyone can get this idea. So two things that affect the amount of work done. It is the force acting on an object, number one. Number two, it is the displacement of that object. In physics, when you're dealing with an object on a horizontal surface, so this is your surface there, and the object is here, and the object is moving, on a horizontal surface, it means to me, in this case, that it's moving on delta x. So this is why I said the force acting and the delta x are the ones that are affecting the amount of work done on the object. So that's basically the introduction just of the concept of work. We keep going. Note these important things as I pull through. All right, perfect. Now, how do we calculate work? What is the formula for the work done on an object? The story. The work done on an object is equal to the force acting on an object, which is F, multiplied by delta x, the displacement of that particular object, multiplied by cos theta. Now let's go through what each one of them means. Number one, we go. The W stands for work, and work is measured in joules. It's very important in physics to be able to write the units of measurement. Work is measured in joules, given by the letter J. I want to just add this as well. The work or work in general is a scalar quantity. Let me clarify what that means. A scalar quantity is a quantity where you consider only magnitude. You're dealing with the size. You are not dealing with the direction. You see, when you deal with vectors consider magnitude and direction. So with a vector, I need to know how much, and I also need to know what the direction is. But with a scalar, I'm only concerned with the magnitude. So when it comes to work, work is a scalar quantity. We just write the magnitude. Example, 20 joules, 30 joules. No need to put the direction because work is in joules and it's a scalar quantity. Perfect. Next up, F. F is the force that is acting on the object. It is measured in newtons. That's the force. Delta X, definitely the displacement. In some places or some particular books, they write displacement as D, but you can write it as delta X. Now, the interesting one is theta. I know it's cos theta, but the interesting one is theta right there. What is theta? Theta is the angle between the force vector and the displacement vector. That's what theta is. The angle between the force vector and the displacement vector. What do I mean? Say for an example, you've got an object right there, and there's a force acting on the object, and the object is moving in the same direction as the force. The theta is the angle between the force, which is this one, and the displacement of the object, which is this one. This is what theta is. The angle between the force and the displacement vector. That's what theta is. And I will be able to show you the values of theta as we go along. So let's go further on that one. So I know the formula now. W is F delta X cos theta. Sharp. Work done can be positive. I want this cleared up. The work done on an object can be positive. The work done on an object can be negative. The work done on an object can be zero. That's basically what I need you to know. So work done can be positive, can be negative, can be zero. Let's discuss the scenarios. When is work done positive? Work done is positive if the force or the component of the force acting on the object moves in the direction of motion or displacement of the object. Let me clarify what that means. So here's a diagram just to show you how it looks like. So you've got the force, okay, and the displacement of the object. They are both moving in the same direction. So in that case, work done is positive. I need you to also understand this. When the force and the displacement are acting in the same direction and the work done is positive, then it means that the positive work increases the velocity of an object, and consequently, it increases the kinetic energy of an object. Let me pull that through for you. When an object has force acting on it, and the force is acting in the same direction as the displacement, what it means is that the work done is positive. And when the work done is positive, there's an increase in the velocity of the object. When you say increase, imagine it in just simple English. The object moves faster in the presence of positive work. And because velocity, movement, speed is associated with kinetic energy. Kinetic energy, the formula being half the mass of an object, velocity squared. Now, because the object has got an increase in velocity, the kinetic energy will also increase. So positive work increases the kinetic energy of an object. Let's break it down further. Let's see negative work. Now, on the flip side, negative work. Negative work is done on an object when the force that acts on it acts in an opposite direction to the displacement of the object. What it means is that the object is moving to the right, as an example, but the force acts to the left. So object, you move to the right, but when a force, you act to the left. What it means then is that negative work is being done. And so what does that imply? When negative work is done, it decreases the velocity of the object as well as the kinetic energy of an object. So in the presence of negative work, we can say the objects move slower. There's a decrease in the velocity as well as the kinetic energy of the object. The diagram that follows now will be able to show you how negative work would look like. So you can see from that diagram that the force is acting to the left, but the object is moving to the right. Therefore, negative work is done. Objects move slower. All right, break it down. Here's a typical situation again, which is quite interesting, where you can see both negative and positive work being done. Two men are pushing. I think they're trying to push this pole against one another. So in this case, this one is doing positive work because he is applying a force. There it is. And this pole is moving in the same direction as this particular force. And on the other side, this man is applying a force. That's true, but the direction of the pole is moving opposite to the force that is exerted. So in this particular case, we can conclude that the man on the right doing positive work, why? Force acting, direction of displacement, the same. There's an increase in the velocity, an increase in the kinetic energy. The man on the left is doing negative work. Why? The object is moving to the left, but the force is applied to the right, decrease in velocity as well as decrease in kinetic energy. Positive, negative work. Let's keep learning. Hope everyone is still okay. Allow me to just lay down the lesson for a couple of minutes. Then from there on, we can be able to start to do the questions. Right. Earlier on, we spoke about theta. Theta, cos theta, theta, the angle between the force and the displacement. We need to understand what theta means. All right. So we stated that it is the angle between the displacement of the object and the force acting on it. That is theta right there. The value of theta, and I put it in bold letters, the value of theta depends on the direction of the force and the displacement. The value of theta depends on the direction of the force as well as the displacement. So what do I mean? Where is the force acting? Okay. And where is the object moving? Okay. That will give me the value of theta. Here are the scenarios. Check this out. When the force and the displacement are in the same direction, theta is 0. Let me read that again. When the force and the displacement are in the same direction, theta is equal to 0. Perfect. We go further. When the force and the displacement are in opposite direction, theta, the angle between the force and the displacement, will be 180. I'm learning. What else? When the force and the displacement are perpendicular to each other, in this particular case, then theta would be equal to 90, just like that. So I need to get these 3 scenarios and visualize them from a diagram setting. So from a diagram setting, here's what the story is. The story says to me, the force and the displacement in the same direction, theta is 0. And then I remember that when force and displacement are in the same direction, positive work is done. So positive work is done when theta is 0. Keep that in mind. Then also, if the displacement and the force are opposing, then theta is 180. And in that scenario, negative work is done. Okay. Now, the last point, which you see here, says when force and displacement are perpendicular. Perpendicular means the angle between them is 90. When the force and the displacement are perpendicular to each other, no work is done. All right, let's do some maths just to clarify this. Mathematically, when you put cos as 0 here, cos 0 is actually a positive 1. Positive work, theta is 0, cos 0 is 1. When you put cos as 180, so that's cos 180, mathematically, this becomes negative 1. So negative work is done. Finally, when the force and the displacement are perpendicular to each other, when theta is 90, and you put cos 90, mathematically, it gives you 0. So no work is done in that particular scenario. So I'm hoping that people understand, when do we do work? When is work positive? When is work negative? Right there. All right, so we continue as we learn some more. So now I know. Okay, perfect. Let's go further. Now, under the scenarios that we've spoken about, I want us to go on further and clarify the conditions when work done is 0. Now, when work done is 0, it happens when there is a force, but there is no displacement. So the force is acting on the object, but there is no displacement. So there is a force. I see that force is available, but there is no motion, no displacement. So if you consider the formula, work is F delta X, then that's cos theta. When is work done 0? In this scenario, there's a force checklist. My force is there, but what's going on? There is no displacement. There is no movement. Delta X is 0. And by conclusion, it means the work done will also be 0. So now I know when force and displacement, or when force is there, but there is no displacement, work done is 0. It's the similar way that you see in the diagram there when someone is trying to push a wall. As you can see for yourself, there's a force that is exerted by Mr. X Kolani here, but the wall is refusing to move. No motion in this particular case. Perfect. That's what you have, just like Umjolo. You're trying to push, but there is no motion. So the work done is equal to 0. You guys always relate to those particular examples quite well. I'm ready for my next one. So work done is 0, under those particular scenarios. All right, where else? The story. The force exerted when it acts perpendicular to the displacement, then work done is also 0. Now, under this scenario, what it means is that theta is equal to 90 degrees. And so because theta is 90, cos 90 is 0. Therefore, at the end of the day, you will pull through and understand that the work done will be equal to 0. Here's a scenario when work done is 0. Now, there is a force, true. There is displacement, true. But what? The force and the displacement are acting perpendicular to each other. The force and the displacement are acting perpendicular to each other. So therefore, in that case, cos 90 is equal to 0 right there. Okay, good. So that's when work is not done. Perfect. Let's try our next scenarios and learn this whole concept of work, energy, and power. I'm still dealing with work for now, so let's work it out from there. I'm ready for my next one. Now, let's start off with an interesting concept. The concept of friction. Frictional force as we know it. This is one of the most important things we will deal with today, frictional force, because it's available everywhere and is an essential part of today's topic. What do I need to know? By definition, frictional force is a force that opposes the displacement of a particular object. That's what frictional force is. A force that opposes the displacement of an object and acts parallel to the surface the object is on. It opposes the displacement, that's true, and also acts parallel to the surface the object is on. Here's a classical definition of frictional force. Bold letters, I'm reading. It is the force that acts opposite to the direction of motion of the object and is parallel to the surface the object is on. Now, I want this clarified because ideally, there is a mistake that is made where it is thought that frictional force opposes applied force. That is not necessarily true. Frictional force opposes displacement. That means if the object is moving to the left, frictional force acts to the right. If the object is moving up an incline, frictional force acts down that incline. Frictional force opposes the direction of motion of an object and also is parallel to the surface the object is on. What do I mean by this? Follow my lead. Object, there you are. And then I've got my particular horizontal surface for now, yes. And then I'm moving. So the object is moving. Let's say it is displacing to the right. That's where the object is moving. The force of friction, and by the way, this is the symbol for friction, FF, or you can just put a small letter F. They mean friction. This is opposing the displacement going to the left, friction, the object moving to the right. And by what we said earlier, I can then conclude that actually frictional force does negative work on an object. Frictional force decreases the velocity of an object. Frictional force decreases the kinetic energy of the object. The angle theta between the force of friction, this one, and the displacement, that one, is 180. In the presence of friction, objects move slower. In the absence, they would move faster. But in the presence, because friction does negative work on an object, because friction decreases the velocity of an object, decreases the kinetic energy of an object. It's a dissipative force. Keep that word in mind. It's a dissipative force. It works against the progress of an object. Object moves to the right, but frictional force acts to the left. Keep that in mind. Dissipative in nature does negative work on an object. So I just put that across again. It does negative work on an object. I like that. What else am I learning? Here's a diagram. So there's a man pushing right there with all his might. Therefore, pushing force, the object moves also to that particular left. But check out the friction. The force of friction is acting opposite to the displacement. Similarly, again, we have a scenario right there where if the motion is this way, then please know that the friction is that way. So in the exam, they use words such as rough surface. So every time you hear an object moves on a rough surface, what it means is that there is friction available on that surface. So that's the terminology that is used in the exam. Okay, I'm ready. I'll move on to my next thing. All right, good. Now, there is a topic that we are going to do. The topic is called Application to Newton's Laws. It's a grade 11 topic. And in that topic, we speak about friction, but more in detail. In that topic, when we deal with it, we speak about two types of frictions, kinetic friction and static friction. For the sake of our lesson in the context of what we need to know, I will speak only about kinetic friction. The word kinetic is a Greek word that means movement. Kinetic, motion, kinetic. I am moving, I'm changing position. I was at A, I am at B, I am moving. Kinetic frictional force. What is that? So kinetic frictional force in essence is written as Fk. So if you see it on the diagram on the board there, it's written Fk, kinetic frictional force. So how do I handle this whole thing? It means to me in kinetic frictional force, it is a force that opposes the motion of a moving object relative to a surface. That's what kinetic frictional force is. The force that opposes the motion of an object relative to a particular surface right there. So this is Fk. And in terms of how you deal with it, let me show you. You see, when you have a scenario like this, so you see from here on, and there is the kinetic friction that is appearing. The ball is moving, so there's movement right there. And when the ball starts moving, the type of friction that is available is kinetic friction. So in essence, the moment an object starts to move, then we can conclude that the force that is acting as friction is kinetic. So I will use these words loosely today. So when an object is moving, I will say friction, but in essence, I am saying kinetic friction. So even if I say kinetic friction or friction, I'm talking about the same thing, because in the context of what we're doing, we're dealing with objects that move. And when objects move, the only force that acts on them is definitely going to be kinetic friction in that context. Perfect. Let's go further. How do I calculate this? All right, there you are. How do I calculate the kinetic friction? It depends on the surface that you are dealing with. When you're dealing with the horizontal surface, the formula is this. It says to me, Fk is equal to mu k. So Fk is equal to mu k. So then the question is, who is this mu k? Who's this one? So Fk, there you are, is equal to, let me write it a bit bigger, is equal to mu k n. All right, perfect. So mu k is called the coefficient of kinetic friction. The topic where this is discussed mostly is application to Newton's laws, which I will teach you. So the mu k is basically the coefficient of kinetic friction. Just know that for now. N stands for the normal force, and on a horizontal surface, the normal force is basically the mass of an object multiplied by its particular gravity. So it's mg. That will be normal force. So Fk on a horizontal surface is this. I did put the formulas, and I just want to reiterate them here because I did put them for you. So Fk is mu kn, and the n is mg. On an inclined plane, and so someone is asking, what is an inclined plane? This is an inclined plane. On an inclined plane, this is your scenario of how to calculate the force of kinetic friction. The formula says the following. It says to me, Fk is mu kn, but it becomes more specific. It says Fk is mu k mg cos theta. This is how you calculate the force of kinetic friction on an incline. The theta, please don't confuse them. Earlier on, we spoke about theta as the angle between the force and the displacement. We did speak about that, right? But then, in essence, under this condition of Fk, the theta is the angle of inclination. And I did put this in part of my notes, that the theta is the angle of inclination. It is actually this particular angle right here. That's theta. So depending on your scenario, am I dealing with the horizontal surface? If the answer is yes, then please know that the formula is this one. Am I dealing with an incline? Yes. Then the formula for calculating the kinetic frictional force would be mg mu k mg cos theta, where theta again is the angle of inclination. Please don't confuse the theta for this and the thetas of 0, of 180, and of 90. Don't confuse them. Now, in the exam, they'll give you enough information. And as we do the questions, you'll see how all of this highlights and becomes a bit easier. All right, perfect. So we're still dealing with the concept of work. And again, I emphasize, if you have any question, please be able to ask me. I will be able to help you out to the best of my ability. All right, let's go. Forces, conservative and non-conservative forces. Your syllabus requires you to be able to define them, not just that, but also to give examples of conservative and non-conservative forces. Okay, I have a diagram. Before I do the definitions, let's interrogate the diagram. I have a diagram, and on the diagram, I've got 2 points. I've got point A, I've got point B, and there's path A, so which means I can move from A to B using path A. I can also move from A to B using path number 2 or path number 3 or path number 1, whichever. But the point is I'm moving between point A and point B. Please get that right. Between point A and point B, I can move using path 1. I can move using path 2. I can move using path 3 between the 2 points. Let's define conservative force. So let's get this right. We need to get the idea, 2 marks in the exam, conservative force. I want to make sure that this is clear. Please note that your exams, definitions are 2 marks or 0. Either you're going to get the full definition or you're going to get nothing. So there's no in between. I know a bit of it. half of it, a quarter of it. You need to get the full definitions of these particular concepts. Conservative force. A conservative force is defined as a force for which the work done between 2 points on an object is independent of the path taken. Let me clarify what that means. So I'm dealing with the conservative force. What does that mean? It means the work done, so it is the work done between 2 points on a conservative force situation is independent of the path taken by the object. What it means is that whether you take path 1, path 2, path 3, a conservative force does the same amount of work on you. The actual path taken by the object makes no difference. So again, a conservative force is a force for which the work done between 2 points on an object is independent of the path taken. The actual path taken does not matter. Whether you go from path 1, path 2, path 3, whatever path you take, it has no significance on the amount of work done. The work done is independent of the path taken by that particular object. That is conservative. So what are the examples? Okay, gravitational force, electrostatic force, magnetic force, elastic force are all examples of conservative forces. I did put a statement as well here to talk about mechanical energy, but I'll pick it up when I speak about mechanical energy in detail. For now, I've just defined conservative force and I've given examples of conservative forces. We keep going on with this one. All right, perfect. Non-conservative. How do I define that? It is a force for which the work done on an object depends on the path taken. So when you deal with non-conservative, the actual path that you take matters. So if you take path 1, you get a different work done. If you take path 2, you get a different work done. If you take path 3, you get a different work done. Hence, if you see at the bottom of my diagram here, I did put the idea that if you are dealing with non-conservative, the work done with path 1 is not the same as the work done with path 2 is not the same as the work done with path number 3. So work done by path 1 is not equal to work done by path 2 is not equal to work done by path 3 in a non-conservative force. If it's conservative, as we had said earlier, the work done is the same. The path taken does not matter. Examples of non-conservative. Non-conservative forces, the best example is friction. So frictional force is a good example of a non-conservative force, right? So that's frictional force. So in this case, what I'm saying is that the work done by friction will depend on the length of the path taken by the object. The longer the path taken, the greater the amount of work done by friction. So it's non-conservative in nature. I did put other examples, and you can see from the left-hand side that we have air resistance, keep this in mind, tension force, we keep that in mind, applied forces, all these are examples of non-conservative forces. Beautiful. We keep moving. I did again put stories on mechanical energy, but I will speak about it as we go to the questions. Okay, good. So far, talk to me. Are we okay? Are we fine? We just want to make sure that we pull through. All right, I'm hoping everyone is okay. Let's keep working on our story. All right, good. Here's my story. we continue. There's a concept called net force. A concept called net force, right? Net force is the sum. When you say net, you're talking about sum of the forces, S-U-M. It is the sum of the forces acting on an object, right? So that's what net force is equal to, sum of the forces acting on an object. So here's a scenario so we can visualize what's going on. And I need you to get this right, that is the vector sum. And when I say vector sum, you are sensitive to direction. Remember that force is a vector on its own. And so when you say vector sum, you are sensitive to the direction that the forces are acting. So what is net force again? It is the vector sum of forces acting on a particle or a body. Sometimes it's called net force, sometimes it's called resultant force. Whichever way is still fine by any means. Okay, good. Then what? When it comes to issues of net force, say you've got three forces acting on an object, force 1, force 2, force 3, they're acting on an object. The net force will be the sum of force 1 plus force 2 plus force 3. So you just simply add the forces. F net is just F1 plus F2 plus F3. All right, perfect. But what is it that I want to show you? Look at the diagram that I put below. This diagram shows different forces. They have been labeled, and I want you to know in the exam, you need to label them according to the approved labels. So what's the story here? There is an applied force, which is given by FA. FA stands for applied force. And this applied force, according to what I see on the diagram, is acting to the right. FA, applied force. There is a frictional force, which is opposing the displacement. You see, because of the presence of FF, frictional force, we can then conclude that the object is actually moving to the right because friction is acting to the left. Fine. There is the normal force, Fn. These are the approved labels. You can say Fn or you can say N, doesn't really matter. Then there's also the downward force, which is basically your Fg, which is force due to gravity. So these are just forces acting on an object. Now, when again you're dealing with net force, all you're doing is you're adding. So I am saying Fa plus Ff plus Fn plus Fg. I'm adding all the forces that are acting on this particular object. But there's more to the story. As it goes further, notice the following. The object, when it is moving at constant velocity, please note this very important piece of information. So the questions will say an object moves up an incline at constant velocity. It moves to the right at constant velocity. When an object moves at constant velocity, here are the implications. Here's what it means to have an object moving at constant velocity. Number one, it means the object does not accelerate. Constant velocity means there is zero acceleration. And let me give you context. The definition of acceleration is rate of change of velocity. So velocity must be changing for us to have acceleration. But when velocity is constant, then we are not changing on anything. The change in velocity is zero. So it means at position A, my velocity will be the same as position B. There is zero change in the velocity of the object, so the acceleration will also be zero. So the implication of the phrase constant velocity is that acceleration is 0. What else? Follow my lead. It means to me as well that the F net is 0. The net force is 0. So net force is 0 when the object is moving at constant velocity. This is taken from Newton's second law, which says F net is ma. And so if a is 0, then F net is also going to be 0. So note these implications. Third, the work net is also 0. I will speak about work net as to what you mean when you say network in physics, what you mean when you say network. But for now, under the concept of constant velocity, the object does not accelerate. The object's net force is 0, and work net is also 0. So it means the F net can be 0 under what scenarios? When the object is moving at constant velocity. All right, perfect. So this was work, the whole concept of work, but the topic says work, energy, and power. Let's go to energy. Okay, how do you deal with energy? Now, in this topic, it's not too difficult because we speak about a very important theorem known as the work-energy theorem. The work-energy theorem is probably the most used formula. You need to be able to state it in words and be able to use its formula. And it's the one that I will use a lot when I start doing questions not so far off from now. Let's break it down. Now, the theorem gives the idea, right? Put it across, maybe I want this part here, and what it states. Okay. It states that, let's concentrate on the right-hand side of our screen. It states that the net work done on an object is equal to the change in the object's kinetic energy. So when you speak about net work, you're saying the net, or rather, when you speak about work energy theorem, you're saying the net work done on an object is equal to the change in the object's kinetic energy. That's just in words. How about as a formula? As a formula, it's work net is equal to delta K. We can go further. It's equal to half mv F squared minus half mv I squared. This is what is known as net work done on a particular object, equal to the change in the kinetic energy of the object. Now notice it's half mass Vf squared, where Vf is the final velocity of the object, minus half mv I squared, where I is the initial velocity of the object. So this is how it is written in words, and this is how it is written as a formula. So your syllabus requires you to state it, but more importantly, to use it. And we're going to use it not so far off from now. All right. I'm gliding to my last parts as we are about to do questions. I'm more excited about the questions more than anything else. This is just the theory, just to help you to be able to understand what you need to know. I'm ready. Free body and force diagrams. The free body and the force diagrams. So you are asked to sometimes draw free body diagrams, and these diagrams give an idea of the forces acting on an object, as well as their directions, as well as their magnitudes. Free body diagram. Let's clarify what it means. Number one, when you're dealing with the free body, it means the forces that are acting on the object are represented by a force diagram of free body. The free body diagrams are used to show the relative magnitude and direction of all forces acting upon an object in a given situation. Further on, the size of the arrow in a free body diagram reflects the magnitude of the force. Let me clarify what that means. So you represent these forces using arrows. So if the arrow is longer like this, then it means it is a greater force. But maybe if it's shorter like this, then it's a smaller force. So the size of the arrow indicates the magnitude of the force. Perfect. We go further. The direction of the arrow shows the direction that the force is acting. So if the arrow is pointing to the right, the force is acting to the right. Arrow is pointing upwards, the force is acting upwards. So goes the story. All right. Each force arrow in the diagram is labeled to indicate the exact type of force that is acting. So as an example, let's say you've got the applied force and it's acting to the right. You label what it means, FA. So that's what it means, FA. Sometimes you can have a string and there's a force on the string, a rope or a cable. That one you write tension, which is given by T. So it will depend on the scenario that you have. Tension given by T. Right, perfect. Also, and there's more notes on this, listen to this. This is very important. The subtopic at the top says free body and force diagram. So how do we differentiate? If it's a free body diagram, then the object is represented by a dot. Free body diagram, object represented by a dot, just like what you see there. The dot there, that black dot, represents your free body diagram. If it is a force diagram, then the object is represented by a box. So the box, force diagram. The dot, free body. Don't make the mistake in the exam. Read the question properly. If they say free body, you show by the dot. If they say force diagram, you represent the object by a box. So basically, that's what you have. These free body diagrams are super important in being able to analyze a question. In fact, free body diagrams are probably the most important diagrams in calculations. They help you to visualize which direction the object is moving and which forces are positive, which forces are negative, and then you can come up with the proper calculations. And I'll show you now when we're doing the scenarios that you may find in the exam. All right, perfect. Let's deal with the scenarios that you may find in the exam. Here's scenario number one. I'm going to talk about two scenarios, then we talk about power, then we start the questions. Scenario number one, what can I find in an exam? You are given that a force acts on an object on a horizontal surface, and it causes the object to move to the right. So there's a force acting on an object on a horizontal surface, and it causes the object to move to the right. So how do I deal with this? So as you can see here, right, there is the applied force, which is there. There is the force of friction. There is the normal force and the force of gravity. This is an object on a typical horizontal surface. So what are the implications? How do we deal with the calculations? Remember, I said the object in this case is moving to the right. Perfect. So what does it mean? What are the implications? Here are the implications. Let's start with net force. The net force that acts on an object is the sum of all the forces acting on it, which then is FA plus FF plus FN plus FG. That is the net force. But I also need us to understand that the FN and FG are equal and opposite, and therefore they cancel each other. Say, what do you mean? I'm saying this FN, this FG, they are equal and opposite, so they cancel each other out. So there will be, one of them will be facing upwards, is positive, the other one facing downwards is negative, and so they're equal and opposite, so they cancel each other out. I'm building up a story here, so follow my lead. Perfect. Then what you're left with is FA plus FF, since FN and FG are equal and opposite and they cancel one another out. Perfect. As we go further, notice that the FA, force applied, is positive. What do you mean, say? If the force is acting in the same direction as the displacement, the applied force is acting this way, the object is moving to the right, so the force and the displacement are in the same direction, then it means FA would be positive. In the same stretch, FF should be negative. Why? The force of friction is acting to the left, but the object is moving to the right. So definitely the force of friction would be negative. And so when you write it down, as you complete it on the net force, you would say to yourself, follow me, you would say F net is FA minus FF. So what you would have done is this. Let me help you understand this. You would have said, okay, FA, you are positive, plus negative force of friction, which eventually mathematically is FA minus FF. So let me see what I'm learning. I'm learning that the direction of motion of an object, if it's the same as the one for the force, then that force is positive. And if the force is acting opposite to the direction of motion of an object, then that force is negative. So in this scenario, which you can find in the exam, you've got F net as FA minus FF. So I've dealt with network. I'm trying to give you an idea of how the calculations would look like. All right, perfect. Let's go further. So that was just F net, but there's more. Let's try net work or work net. Still our same scenario, our same diagram that we're looking at, but this time we're talking about network. Now, net anything, net work, net force, net whatever, net anything is the sum of the concept. So when I say network, is the sum of the works done on the object. Now let's be clear. The forces do work. When I started my lesson, I said each force does work. So there's work done by applied, work done by friction, work done by normal, work done by gravity. Each force does work. That's what I need you to know. Each force does work. So when I speak about network, I'm talking about the work done by the applied force, the work done by friction, the work done by normal, the work done by gravity. Each force does work. But let me go further. The work done by the normal and the force of gravity is zero. I'm reading. Since the forces act perpendicular to the displacement of the object. So let me give you an idea of what I'm saying. Follow this thought process. As an example, say you're looking for the work done by normal force. It will be Fn delta x cos theta. Then notice that we say the object is moving to the right. That's where the object is moving. So therefore, the normal force and the displacement of the object with theta, or rather displacement of the object and the normal force, are acting perpendicular to each other. Theta becomes equal to 90. Cos 90 is 0. So the work done will be 0. They love asking this question where they say to you, why is it that the vertical forces do no work on the object? This is because theta is 90, or this is because they act perpendicular to the displacement. Theta is 90, cos 90 is equal to 0. That's what it means when you're dealing with this particular situation. Therefore, here's where we are. Work done by applied, work done by friction. Okay, let's go further. The formula for work is F delta X cos theta. So when I'm being contextual, the formula for work done by applied force is FA delta X cos theta. The work done by friction is FF delta X cos theta. Now, theta. Oh, listen to this very carefully. Theta. Listen to this. The theta for applied force, whereby the object is moving to the right, the theta for the applied force would be 0. Because the force and the displacement are in the same direction, theta is 0. The theta for force of friction, whereby force of friction is opposing the displacement of the object, the theta for force of friction would be 180. Okay, so when you see it on an equation format, here's how it would look like. Work net is FA delta X cos 0 plus FF delta X cos 180. And here's a classical mistake that is sometimes made. The classical mistake is you already can see that you've put cos 180. And then someone says, oh, but say when you say to us that friction is negative. So let's say they gave you friction as 20 newtons. So you say plus negative 20. Let's say the displacement is 6 times 6. Then you say, oh, it's friction, by the way. So it must be cos 180. That's a huge mistake. This is because cos 180 already stands for -1. And you've put a negative here. So now there's a negative. Multiplying another negative is now positive. You've double negated, and that is wrong because the work done by friction can never be positive. It is always negative. So if you insist on putting negative here, then don't put cos 180. Don't put it. But you can't put both negative FF and cos 180 because cos 180 is actually standing for -1. So be clear on that aspect. So this is my first scenario that you may find in the exam. The force acting on objects, or the forces acting on an object that is on a horizontal surface, and the relative formulas for that. Let's go further. All right. Calculations on inclined surfaces. Now it gets interesting. This is where we go down now. All right. Ready? Because I am ready. Here we go. Objects being pulled up an incline. So here's my story. You have an object that is being pulled up an incline, and this is the force diagram and how it will look like. So an incline is where you've got an angle right there. It's not a horizontal surface. And these are the forces acting. There's this applied force is acting up. The object is being pulled up the incline. And because it's going up, displacement, object up, there's this force, which is force of friction, which is acting downwards. And then there's the normal force available, mg, that is the force of gravity. Sometimes you write it as W for weight. It doesn't matter. Either of them is correct. So these are basically the forces acting on this particular object. I want you to notice the following. Please listen to me. The incline is beautiful physics. Why are you saying that? Say, this is because, as you can see, it's FA for F net FF plus FN plus FG. But what? On an incline, the force of gravity is resolved into components, is broken down into two force of gravities. Which one? There's what is called the force of gravity parallel. Which one? There's what is called the force of gravity perpendicular. So on an incline, the force of gravity is broken into two pieces, force of gravity parallel and force of gravity perpendicular. Let me show you how they would look like. Interesting diagram right there. Follow my lead. So here's how the mathematics would work. So you'd have the incline, there it is. And this one is the force of gravity parallel. And so if I were to draw it here, I would put it as a force that acts downwards and is always acting downwards, force of gravity parallel. And then the force of gravity perpendicular is always in the same straight line. And I'm trying to draw a straight line and I'm failing dismally. Let me see. Is always in the same straight line as the normal force. So this will be the force of gravity perpendicular. They all have formulas. The force of gravity parallel is mg sine theta, where theta is the angle of inclination. That's the formula for force of gravity parallel. The force of gravity perpendicular has this formula, mg cos theta, where theta again is the angle of inclination. So when you're dealing with an incline, only with an incline do we have a situation where the force of gravity is broken into pieces. So here are the formulas as I put them across, as you can see, and I put the idea that theta is the angle of inclination between the horizontal and the incline. So when you're now writing, listen to this, when you're now writing your F net proper, before we had written as FG, before I told you that we break it into pieces. Now that I've broken it, it's FG parallel and FG perpendicular. Fine. Now, if you go further, you will notice the following. Listen to how interesting it gets. When you go further, notice that the FA is remaining as a positive force. Why say? Because the object is being pulled upwards. And so the FA is acting in the same direction as the displacement. The force of friction will be negative. Why? Because it's opposing the displacement of the object, force of friction. The force of gravity parallel will also be negative. Why? Because it always acts downwards. I didn't put it in this diagram, but it always acts downwards, force of gravity parallel. And in this case, the object is moving up, force of gravity parallel acting down. So therefore, it's going to be negative. So say, where's my gravity perpendicular? Say, where's my normal? They cancel each other out. They are equal and they are opposite. So they will cancel each other out. And so finally, when you have your formula for this scenario, F net is FA minus FF minus mg sine theta. So I have that and I'm ready to pull through and take it up from there. Okay, good. I'm ready. Let's move on to the next thing. So don't worry, these things I'll show it to you now. When I'm about to do questions. The theory is very important and I need you guys to understand it very well. Because without the theory, we cannot be able to understand the question. So it may take a bit of some time to understand the theory. And then when we do the questions, we'll just glide because at least we understand what we are doing. Let's go to the work net. I've done the first, the F net. Let's go to the work net. Still on the same scenario. There you have it, the same scenario. So who is doing work? Who is doing work? Okay, good. Let's work. The net work is done by the applied, by the friction, by the normal, by the gravity parallel, and by the gravity perpendicular. But notice that the work done by the gravity parallel and by the gravity perpendicular and the normal force, that work done should be zero. This is because they are acting perpendicular to the displacement of the object. Let me try and draw you the free body diagram that I can visualize for this situation where I include our gravity parallel. So free body, there you have it. Just going to draw randomly, so don't worry about the shape and the length. This is your applied force. This is your force of friction. This is your force of gravity parallel. This is your gravity perpendicular. And this is your normal. All right, perfect. And under this scenario, notice that the work is done by all the forces except that the work done by normal and gravity perpendicular should be zero because they act perpendicular to the displacement of the object. Theta is 90 and cos 90 is 0. So who's doing work? It's the work done by the, okay, let me check this diagram out now. Remove this. Is the work done by the applied, the friction, the gravity parallel. Let's go further. Look how interesting it gets. How did I get to this point? Follow me. The work done by the applied, theta is 0 because applied is moving in the same direction as displacement. The work done by friction, theta is 180 because the object is moving up, but friction acts down. So theta is 180. The work done by gravity parallel. Remember earlier we had said gravity parallel as a formula is equal to mg sine theta. So that's gravity parallel. And so the work done by gravity parallel will be fg parallel, okay, delta x, all right, cos theta. I'm trying to show you how I came to that, but I know this guy. This guy is fg parallel, which is mg sine theta. Then we continue times delta x. Then we continue times cos 180. Why? Because the fg parallel will always act downwards. In this case, it will be opposing the displacement. So the angle between them is 180. That's how I ended up coming to this particular formula that you're looking at right there. This one here, that's how I ended up in this scenario. But I want you guys to know that there's so many ways and so many scenarios in the exam that you could actually match up with. So whichever way you look at it, you can match up with any particular scenario from there on. Now, let me go further and clarify. So that's what you have there. And now to the last part, power. Power. All right, still there. I can hear you, I can feel you, and we're working together. Power, as a definition, is the rate at which work is done or energy is transferred. That's how you define power. In terms of a formula, it is power is W over delta T. It is measured in watts. Watts given by W. Power is work done over time taken or the rate at which work is done. So I did put, and remember that work is F delta X cos theta over time and blah, blah, blah. Now, in the case where you've got F and delta X, they're in the same direction. I'm just showing you another formula. You're not required to know how it comes about. I just did put it, but I want you guys to know the two formulas. Is power, is force acting on an object and the velocity of that object, or its power is work done over time taken. The choice of an equation depends on the information that has been given. All right, so that's just power. You just need to know the definition. Just need to know the two formulas that you can use for power, and that's just it. Thank you. What do we do now? we go to the last section, which is tips on what to do when dealing with this, or just a summary of the forces. Yeah. There's the fancy thing going round and round. These are the formulas that you use in this topic, but we will be using them as we go along. Some of the stuff I will teach you via questions, but basically this is the long and short of our topic. All right, the tips to follow when dealing with this is number one, take note of words such as up an incline, down a slope, or to the right, or to the left. Those words are very important. They will help you to understand and visualize the context of what we are talking about. Further on, if the question says the surface is frictionless, then it means the force of friction is not acting on the object, and therefore mechanical energy is conserved. Also, and I'll talk about mechanical energy, on an inclined surface, this is very important, on an inclined surface, force of gravity acts downwards, parallel to that surface. All right. What else do I need? Force of friction is a dissipative force. It works opposite to the displacement of the object right there. That's very important. So it does negative work on the object. All right. Here is what we've been waiting for. Past exam practice questions. Get your calculators out. Let's do this now. So let me start a couple of questions there. I want to make sure that everyone understands. This is the part, honestly, family, that I need you guys to be able to ask me questions. I really need us to interact. So I'll start with a small to medium-sized question, up my game a bit as I do more. Here's a question. Let's work on it together. It's a 2014 Gauteng paper. Paper 1, question 6. I have the handout, so that's why I put the page number. So you're in my group, so I'll send the page number or the pages to you, or the handout to you rather, so you can know what to do. I'm ready. The story. So write down the title and the page number, or just the title itself is fine, and then we will take it up from there. So work, energy, and power, the questions. I'm ready. Let's do physics. Let's read the English, the story, break it down so we don't have to suffer when we are answering. A cyclist pushes his bicycle of mass 6.1 kgs up an incline, up an incline. I told you, take note of these words. With a force of 20 newtons, numbers. The bicycle is pushed from an initial velocity of 5 meters per second from point A, I see point A, to point B. The road is inclined at 10 degrees to the horizontal, and the distance from A to B is 32 meters as shown below. Okay, I see that. Then it says the road surface exerts a force of friction of 11 newtons. I'm dealing with my numbers on the bicycle tires. 6.1, 3 marks. Calculate the work done by the cyclist on the bicycle. Work as a formula is F delta X cos theta. You're given a mark for writing the formula. So we're looking for the work done by the cyclist. Let's get the force of the cyclist. The force of the cyclist is 20 newtons. So that's 20. How far did the bicycle go? Delta X is 32. Then I need to have my cos. Notice that the direction of displacement of the object and the force exerted by the cyclist, they're in the same direction. So theta is actually 0. And so when you do your maths together, your answer is 640 joules. That's your answer right there. Please write that one down. We are dealing with the force and the force done by the cyclist, and we want to find the work done. So you get a mark for the formula, get a mark for the substitution of the values. You also get a mark for the answer, which is inclusive of the units. 3 marks, we have it. Let's try 6.2. 6.2, I may need your help in the calculation for 6.2. I'm taking this out. It says to me, use the work energy theorem to calculate the magnitude of the velocity of the bicycle at 32 meters. So by the time it gets to 32 meters, this bicycle is at point B. Use the work energy theorem. Now, the work energy theorem says work net is equal to delta EK, which is kinetic energy. And so I need to think about what's going on. For me, what is key is the free body diagram. This is because the object is moving up an incline. Remember the scenario that I finished with? We said up an incline, so these are the forces available. There's the applied force, the force of the cyclist. The force of friction is there. There's the force of gravity parallel, which is always acting down. There's force of gravity perpendicular. There is also the normal force. So this is the combination of forces available. Now, since we're dealing with work net, we need to know which forces are doing work. It is the applied force doing work. It is friction doing work. It is gravity doing work. Normal and gravity perpendicular are doing no work at all. Answer, because they act perpendicular to the displacement. So the guys doing work is the applied plus the work done by the friction plus the work done by the gravity parallel. All this is equal to a half mv f squared minus a half mv I squared. All right, perfect. Let's put numbers now. We did speak about work done by applied. Okay, let me do it old school and write. It's FA delta X cos theta. Work done by friction, FF delta X cos theta. Work done by gravity parallel. Let me do it the way. mg sine theta delta X cos theta. All this is equal to a half mvf squared minus a half mvi squared. The numbers now. FA, we're told that it is 20 delta X 32 times cos 0, because the applied force is moving in the same direction as displacement. And we did find this work done by applied in the previous question anyway. The force of friction, we're given that is 11 multiplied by 32 multiplied by cos 180. I'm now here for work done by gravity parallel. The mass is 6,1. G is 9,8. That's gravity, gravitational acceleration. Sine theta, don't forget this. The theta is the angle of inclination. So this is sine 10 multiplied by delta X, which is 32, multiplied by cos 180. This is because the force of gravity parallel is acting downwards while the object goes up. Perfect. Then it's a half, sorry for the small handwriting, 6,1 squared, 6,1, sorry, it's mass, times VF squared minus a half times 6,1. They said the initial velocity was 5 meters per second, so that's 5 squared. So what am I looking for? I'm looking for VF. So the only thing that I don't know is VF right there, right? I asked you guys, if you feel like it's blurry, it could be your network. You can always zoom in your screen. You'll be able to see what I'm talking about. Zoom in your screen, you'll be able to see stuff. Mathematically, everything is fine. And then the only thing that I don't know is VF. So to find VF, it's going to be 3,24 meters per second. I don't have time to do the actual math, the numbers, the calculator. The answer is specific. It is 3,24. Zoom in your screen. You'll be able to see what I am talking about. Okay, let me know when there are any questions. Right, none so far. All people are writing this. Let me give you a couple of seconds, or you can just take a screenshot. It's still basically easier that way. And let me just take the screenshot thing, or you can take the screenshot thing. Thank you so much. I hear the responses. People are saying, clear, say, we're good. I like that. So to do more, let's take the screenshots, fam, and let's work it out from there. Okay, gone. 6.3, explain why frictional forces are regarded as non-conservative forces. Explain why frictional forces are regarded as non-conservative forces. I think we can think the idea, Uti, because the work done by frictional force depends on the path taken by the object. So maybe write the following. The work done by the frictional force depends on the path taken by the object. So that's why they are called non-conservative. Work done by the frictional force depends on the path taken by the object. All right, let's get down to bigger things. All right, here's another question. So there are 6.3 from the previous one. Work done by frictional force depends on the path taken by the object. All right, somebody's asking me to repeat 6.2, where mg sine theta and delta x cos theta. All right, sharp. Let me just go back just a bit there. Let me see if I can relive. Yes. So the work done by gravity parallel, I need you to remember that it is always mg sine theta delta x cos theta. So let me take everything out. Work done by gravity parallel is always fg parallel delta x cos theta. Now, in this particular aspect, the fg parallel is mg sine theta, then we continue again, delta x cos theta, and U theta is 180 just for this scenario because the object is moving upwards, but gravity acts downwards. That's why I put it like that. I'm hoping that you understand this time as I try to go on. Here's an interesting question. 2015 March, please write down the title, and I'll send the handout as well. A 5 kg block is released from rest from a height of 5 meters and slides down a frictionless horizontal portion PQ, and finally moves up a second rough inclined plane. It comes to a stop at point R, which is 3 meters above the horizontal. So there's my diagram. If you notice the questions, the last question is 7 marks. So we'll think a lot. And I want us to be able to understand the scenario from scratch, so work with my line of thinking. The 5 kg block is released from a height of 5 meters. Okay. And it slides down a frictionless incline. They said that to me. So the incline has no friction. Then it gets to point P. Then it moves along a frictionless horizontal portion, PQ. And finally, it moves up a second rough inclined plane. So from the start to Q, there's no friction. But QR, the second incline, is rough, and rough means there is friction between Q and R. It comes to a stop, so it stops at point R, which is 3 meters above the horizontal. So it stops at point R. Perfect. And so here's what I need to teach you. Let me start this way. There's a concept in physics known as mechanical energy, or you can say EMAC. Mechanical energy basically is the sum of the potential energy and the kinetic energy on an object. That's what mechanical energy is. So potential energy is mgh as a formula. Kinetic energy is half mv squared. Now, what it means for potential energy is that it's the mass of an object multiplied by g, gravitational acceleration, multiplied by h, which is the height of the object above the ground. Kinetic energy is half mass of object, v squared, that's fine. V being the velocity. So that's mechanical energy. Now, mechanical energy can be conserved. This word is very important. Conserved. What does that mean? It means the mechanical energy at a certain point, point A, will be the same as the mechanical energy at a certain point, point B. If they are the same, if they are conserved, what are the conditions? For mechanical energy to be conserved, the system must be isolated. This is giving me the vibes of momentum and impulse. So when the mechanical energy is conserved, the system is isolated. What does it mean when you say a system is isolated? There are no external forces acting on the system. Say, what do you mean? I mean that the system is frictionless. When you go to my tips, when I put the tips, I said, if the word says frictionless, it means there's no friction, and also the mechanical energy is conserved. So in this case, from start, which is this particular point, to point P, mechanical energy is conserved. From P to point Q, mechanical energy is conserved. This is because they are frictionless. There is no friction. The system is isolated. In fact, this gives me an idea of the principle of conservation of mechanical energy, which states that in an isolated system, the total mechanical energy is conserved. So sometimes they ask you that, so please make sure that you know it. So then, now that I know that if it's friction, mechanical energy is conserved, I can start my question. The question underneath the diagram says the frictional force, which is a non-conservative force between the block and the surface, is 18 newtons, which is fine. Use energy principles 5.1. Use energy principles only. Calculate the speed of the block at point P. Use energy principles. So when I do energy principles, I need to use any formula that has energy in it. So what am I looking for? I'm looking for the speed at point P. What do I know? The incline from start to P is frictionless, system is isolated, mechanical energy is conserved. Say, what do you mean? I mean the EMAC at the top. So the mechanical energy at the top should be equal to the mechanical energy at the bottom. Okay, let's get down to business. Mechanical energy is mgh plus a half mv squared. That's at the top. At the bottom, it's the same thing, mgh, but at the bottom, plus a half mv squared. So this is when you're dealing with the top, and this is when you're dealing with the bottom. Let's put numbers now to make it a bit clearer. So the mass is 5, G 9.8. The height above the ground, there's my number, is 5. Plus half mv squared, which will be 0. How do I know? Because it was released from rest. So at point, this one, the object has 0 velocity, so that's 0 kinetic energy. Then here it's mgh, I'm at the bottom, I'm at point P now. It's also 0 y set because the height at P is 0, I'm on the ground. Plus the half mass 5 multiplied by v squared. So this should be v squared there. There you are. And I'm looking for v, the speed of the block at point P. Doing the maths proper, the answer is 9.9 meters per second. That is v, the velocity of point P. All right. So I used energy principles, the concept of mechanical energy being conserved, the one at the top being equal to the one at the bottom. All right, let me take this out. I want to try 5.2. Okay, let me keep it there while I explain 5.2. Explain why the kinetic energy at point P is the same as that at Q. What do you think? Let me hear you. Let me get you guys participating. Explain why the kinetic energy at point P, all right, at point P, all right, is equal to the one at Q. Why? Why? What do you think? Let me hear your submissions. I want to read your answers. Why do you think that the kinetic energy at point P is the same as at Q? Talk to me. Okay, I'm getting the answers now. I love that. Someone says no external forces are acting on the object, therefore mechanical energy is conserved. I love it. I love it. That's exactly the answer that I want. Someone says no friction, loss of EK is 0, which is perfect. That's also a good way to put it across. I like it, and that is also acceptable. So definitely any of these two answers that have been posted, where someone says no external forces are acting on this particular object, so therefore the mechanical energy is conserved. No friction, so loss of kinetic energy is 0. Maybe let me just clarify. There is velocity. The issue is that it is constant. This is why the velocity at P will be the same as the one at Q. So it will be constant because there is no friction, no loss in kinetic energy, mechanical energy is conserved. So I need you to get that there is velocity. So you can't say velocity is 0. What you can say is 0 is acceleration. Okay, remember, because we said when the velocity is constant, the acceleration is 0, and F net is 0, and work net is 0. So hoping that people understand, pull through there. All right, perfect. So the answers are coming. No external forces acting on the object. Therefore, mechanical energy remains the same. 5.3, here we go. Explain the term non-conservative force. Explain the term non-conservative force. I think we've done something similar. We said it is the force for which the work done is path dependent. It is the force for which the work done is path dependent. Force for which the work done is path dependent. All right. I'm ready for 5.4. Calculate the angle theta of the slope QR. That's where the 7 marks comes from. So they want me to calculate theta, which is this angle, and I don't know it. So please listen to me as I pick it up and let me know where you don't understand. I'll go step by step and we clarify. QR is where there is the rough inclined plane. So QR, there's my incline where there's friction. Notice that the object moved from P and went to Q, then it went up, then it stopped at R. So we can then safely say at R, the velocity of the object is equal to 0 meters per second. While here, the velocity is 9,9. Where do I get that from? This is because the velocity at P and the one at Q is the same. Kinetic energy does not change. Velocity does not change. No loss in kinetic energy. Mechanical energy is conserved. So when I go from 9,9 up to point R, I'm going to be reducing velocity until I get to 0. And it makes sense because I say to you, in the presence of friction, an object moves slower. In this case, it moves so slow that it ended up stopping. Sure. Then it says to me, calculate theta. So let me get the free body diagram, which I always say is the most important thing. The force of friction is acting downwards since the object is moving upwards. Also, the force of gravity parallel is acting downwards. There is the normal, there is the gravity perpendicular right there, but there's no applied force. No one told us that the object is pulled up. In fact, interestingly, due to the momentum gained by the object from the incline at 5 kg up to P where there's no friction, and between PQ still where there's no friction, the object moves on its own upwards due to the momentum gained from the start up to point Q. So there is no applied force. Sharp. We know that there is a change in the velocities from 9.9 to 0. And I mean, I'm looking for theta. Okay, sure. If I use work net is equal to delta K, I have some case. I have an idea. Why are you using that say? It's because the work is done by friction. The work is done by gravity parallel only. And so that work done by friction, that work done by gravity parallel is equal to delta K, which is change in kinetic energy. Now, for me to find theta, I need a couple of things: trigonometry, mathematics. Here's the story. If you see theta here, notice that this is a right angled triangle. This is 3 meters, it's part of your diagram. And I don't know this displacement here. It's actually the delta x, which is traveled by the object. So when I deal with maths, I'll say I have opposite and hypotenuse. So sine theta is equal to opposite, which is 3, over hypotenuse, which is delta x. Opposite over hypotenuse. I don't know who delta x, I don't. So I'm clueless. I don't know theta as well. But if I find delta x, I can find theta. Let's do physics. Work done by gravity parallel, or rather work done by friction, is 18, that's friction F, times delta x, which I don't know, times cos 180. Perfect. That's work done by friction. Work done by gravity parallel is m, remember it's mg sine theta, delta x cos theta. M, which is 5, g 9.8 times sine theta. Remember the work done by gravity parallel, let me just reiterate this so you remember. It's always mg sine theta, delta x cos theta. But hold on, I don't know sine theta. I know it is 3 over delta x. So instead of putting mg sine theta, I'll put 3 over delta x. So here, where the sine theta, 3 over delta x, it continues, times delta x. Yes, that's why I wanted it. Times cos 180. Cos 180 because force of gravity parallel is acting opposite to the displacement. All right, all this is equal to the change in the kinetic energy, which is a half mass of the object, which is 5, final velocity, 0 squared, minus a half mass of the object, which is 5, and the initial velocity, 9,9 squared. Okay, say, put a lot of stuff, so what? The delta x and delta x cancel out. Everything else is numbers except delta x. We don't know what delta x is. When you do your maths properly, I won't do it. You guys can try it. The answer is 5,4458. That's delta x. So I used the worknet formula and dealt with the guys doing work. I'm not done. I just found delta x. I'm not looking for delta x. I'm looking for the angle theta. The angle theta. That is exactly what I'm looking for. All right, so let's break it down together. I'm looking for angle theta. You let me know where you don't understand so I can help you out. So delta x has been found as 5,4458. Earlier on, we ascribed that sine theta is 3 over delta x. I know delta x now. It's 5,4458. This reminds me now of trigonometry in maths. I'm looking for theta. So what do we say in maths? Shift of sign. Shift of sign right there. And you are having theta as shift of sign of 3 over 5,4458. And so theta is 33,43 degrees. And that becomes your final answer. So I see someone says, can we have a step-by-step guide on what to do to get the answers? It's just calculator. Do it one by one, step by step. It's just a calculator. Take a screenshot here and I'll show you how to break it down. It's just calculator and all, because I want you guys to know the physics for me, the physics ended here. The rest is not physics, it's maths. The physics ended here. Once I substituted my values, I stopped with the physics. Then from there on, it became mathematics. Write this down. Let me know if there's any question. I need the questions. I'm more concerned about the questions. All right, so now the questions are coming up, which is what I want. Say, why did you not put sine? I didn't, because I didn't know what sine theta is. I knew it as 3 over delta x. So instead of putting sine theta, I put 3 over delta x in its place. That's what I did there. 3 over delta x. All right, let me get another one. Let me read the question. What is it saying? Say, what happened to the v squared? There was all the v's where we had the numbers, because it said it stops at r, so the final v is 0. And then at q, when the journey started, it was 9,9, because it's the same v that we had at p. Since we said it's frictionless, so therefore the velocity is constant. The one at p should be the same as the one at q. So 33,43. That's what you have right there as your theta. I need more questions. Let me know where there's a struggle whatsoever. Someone says my displacement is negative. How so? How the displacement is negative? It should actually be a positive when you do the maths. All right, let me see if I can try and get the maths done and work it out from there. Or somebody says, okay, now you say you got it. Okay, perfect. I like that. Say you got it, so it's fine. All right. All right, let me see another question. I'm getting 10.9 as my displacement. So I think it could be an error somehow. Just really try it, because the actual answer is actually 5,4458. That is the actual answer. Most of the stuff that you guys really struggle with is not really much to do with the actual physics. It's just the maths, putting things on the calculator, and you must be very extra vigilant when you do that. So maybe retry it, you'll get the answer. Somebody says, say if we're asked to calculate using energy principles and there's friction, how do we work it out, right? You can use this. Work net is delta K. When you're asked to use energy principles, anything with an energy in it, formula, work net, delta K, kinetic energy, energy principles, that is what's going to work on that aspect. All right. Is rounding off your answer for delta X advisable? No, it's not. So take the number as it is and round it off at the end, which is what I did here, 5.4458 as far as I could go, and round it off at the end. Answer 33,43. Okay. What else? This is your 7 marks question. All right. So listen up. Basically speaking, this is what work, energy, and power is all about. Now, remember, we're limited with our time, so there's so many questions that I have. My word, I've got so many questions that I have. So for me, this is actually part 1, and part 2 would be when we are doing more questions on this. But I want us to understand this. I do these lessons periodically, right? So I'm not going to be able to move on further from now because our time is literally pretty much gone. But let me explain how I usually work. Maybe write this down for those that are still writing, or take a screenshot, which is what I advise, and all. Okay. Here's the mode of operation. All right, let me do this. Let me take the screen out. Now, on the screen, you should be able to see, if you look at my profile here, it says what I do. So as part of what I do, I know I do these topics, but I don't do them these lessons, but I don't do them every single time. I just do them as and when I feel there's a need. But I do have classes that I have. Over the past couple of months, I've been very fully booked And now I'm starting a new section of classes. I'm still fully booked, but I'm starting a new section of classes from next week, where I'll be dealing with topics, especially for what you're going to write in June. Some of you are in grade 12s. All of you are in grade 12, and your June exams are coming through. So I am going to start through and start revising for June. So I'm revising. I'll be doing many different topics. Trigonometry, I do maths. I also do physical sciences, the very difficult topics and all, for that everyone can understand. But these topics are paid for, or these sessions are paid for. And I will send a poster to detail the days, to detail the monies that you need to pay if you want to attend. This was just free, just for today. And I'm glad people are saying thank you. That's a good African way of behaving. When someone does something nice for you, you always say thank you to them. I will also put my number right now, and I love the feedback that's coming up. I'll put my number so that in case you need lessons or whatever, we can start working on it. The group classes, the ones that I'm going to do from next week, they basically are quite cheap. They're about 100 rands for a 2-hour session. There's my number. And then the Facebook, or rather not Facebook, the YouTube name is Mr. X. I'm typing it. Mathematics. Thank you so much. Love it. And science, grade 12. Also say these nice comments in your groups at school or in the groups that you guys are in. Grade 12, Mr. X, mathematics and science for grade 12. All right. For grade 12. That's my YouTube channel. So I will upload this on the YouTube channel. We can be able to take it up from there. So having said that, fam, this marks pretty much the end of our lesson. And thank you for attending. Thank you for telling other people about this. Listen, I can pretty much help you. I am very good at what I do. I've helped a lot of students to pass very well, from their 20% in the June exams to their 100% or 90s and thereabout. So pretty much you are set when you are with me. So don't worry about anything. So we'll talk soon enough. What I'm going to do, I'm going to upload this lesson on my YouTube channel, hopefully today, hopefully today. If not, I will do it tomorrow. And so you can watch it at your own spare time and all that. But this was just part 1. Part 2 is coming, and I'm going to do part 2 next week, but it's not going to be free. That's for certain. It is not going to be free. So I will send the posters and the topics that I'm going to be doing and everything. If you're interested, you can go ahead and we will talk. My number is there, 073-974-8498, and we take it up from there. Thank you so much for being available today. Have yourself a good night. My name is Mr. X, the original Chuck Norris. I'll see you soon. Good night.